Welcome to The Explainer. Today we're going to talk about a really cool idea from computer science, one that solves some of the most complicated problems you can imagine by copying nature.
So let's start with a challenge. Picture this. You want to build the absolute perfect custom PC. You've got literally hundreds of different parts to choose from. Processors, motherboards, you name it. The number of possible combinations, it's just staggering. You could never test them all. So how do you find the single best one?
Now, what you're looking at here might just seem like a mess of data, right? But believe it or not, this screen holds the answer. This is the output from a program that solved our PC problem, and it did it using a method straight out of Darwin's playbook.
Okay, let's get into it. To really get how this works, we need to take a step back and look at the most powerful problem solver that exists, evolution itself.
You know, for billions of years, life on Earth has been fine-tuning itself. The animals that are a little bit faster, a little bit stronger, they're the ones that survive and pass on their genes. It's this slow, grinding, but unbelievably effective process. So, some very smart computer scientists started asking, hey, what if we could make our programs do that?
And what's so cool is how perfectly the ideas translate. In nature, you've got a population of animals, each with its own DNA, all competing for survival. In our program, we have a population of PC builds, each with its list of parts, competing for the highest score. The ones that are the fittest get to continue. It's a perfect parallel.
So that's the theory, but let's see how this brilliant idea actually works when you put it into practice inside a computer.
Okay, so this is the textbook definition. But what does it really mean? A genetic algorithm doesn't just hunt for one right answer. Instead, it creates a whole bunch of potential answers and basically lets them breed and compete with each other, getting a little bit better generation after generation until a fantastic solution just emerges.
And that is exactly what we were seeing on that screen a minute ago. Every single one of those rows, that's a digital creature, a totally unique computer build. And that column labeled score, that's just its fitness rating. The higher the score, the better its chances of passing on its genes. Or in this case, its list of components.
So, where does it all begin? Well, the program kicks things off by creating an initial population. For this problem, it started with a pool of 20 completely different, randomly generated PC builds. And that right there, that's generation 1.
All right, so you've got your first generation. How does the evolution actually play out from there? And maybe more importantly, how long does this digital version of natural selection actually take?
It happens in this really powerful loop. First, it creates that random population. Then, it tests and scores every single one. The best solutions, the ones with the top scores, are chosen to breed, which means they mix and match their best features. Then, and this is super important, comes mutation. The program randomly changes a few of them. This is how you get new ideas into the mix so it doesn't get stuck. And then, the whole process just repeats with this new and hopefully much improved generation.
And these are the rules for that digital breeding. That 80% crossover rate means the program really favors combining the best parts of what already works. But that tiny 2% mutation rate is absolutely critical. It makes sure that while fresh ideas are always being introduced, the whole process doesn't just spin out into random chaos. It's all about controlled, guided improvement.
So here's where it gets kind of mind-blowing. The program didn't just run this loop a few times. It simulated, get this, 27,573 generations of computer evolution.
And how long do you think it took to go through nearly 28,000 generations? Just a little over 4 seconds. I mean, think about that. In the time it takes you to sip your coffee, this algorithm designed, tested, and evolved tens of thousands of generations of computers to find an amazing solution. That is just breathtakingly fast. This right here is the magic of the whole thing. When you're facing a giant haystack of possibilities, the genetic algorithm doesn't waste its time searching for the needle. It basically evolves the entire haystack into a big pile of needles and then just grabs one. Now, as fun as building a high-end PC is, this technique is being used to crack some of the most complex problems in the world. Its applications are changing industries in ways you probably don't even see.
Yeah, this stuff is everywhere. Engineers use it to evolve the perfect shape for an antenna or a more efficient airplane wing. In finance, they can evolve complex investment strategies. In logistics, a program can figure out the best routes for an entire delivery fleet, saving millions. They're even using these ideas to create art and to model everything from new drugs to the formation of galaxies. It's wild.
So, look, if there's one thing to take away from all of this, it's this fundamental shift in thinking. For a whole class of incredibly hard problems, the best way forward isn't to search for an answer. It's to breed one.
And that kind of leaves us with a pretty fascinating thought, doesn't it? From designing new medicines to fixing global supply chains, or maybe even tackling something as huge as climate change. What other impossible problems are just sitting there, waiting for us to stop searching, and instead, just let the answer evolve?